Valence electrons are important to chemists because they help to determine the properties that atoms will have. Valence electrons are the electrons found in the outermost energy level of the atom. We call these valence electrons, and we can determine how many valence electrons an atom has by the column that it sits in on the periodic table for our main group elements. Any electrons that are in energy levels lower than our highest principal energy level, we call those core electrons. So anything with a lower value is going to be a core electron. And again, these are very important to chemists because they do affect how the atom behaves, and they also affect the type of ion it's going to form or the bonding that is going to occur. We can determine what an electron configuration is by looking at the periodic table. So the group number, the column that it sits in, corresponds to the number of valence electrons. The length of each block is the maximum number of electrons that can be held in that sublevel. So for our first two columns on the periodic table, those are the s orbital. We can put 2 electrons into the s orbital. The period, or the row number, corresponds to the principal energy level of those valence electrons. So whatever row it sits in, those are the energy level of those valence electrons. So let's take a look at what this means. So labeled on the left, we have our principal energy levels. These correspond to the n value on the periodic table. The first 2 columns represent our s orbital, and we can put 2 electrons into the s orbital, 1 spin up and 1 spin down. We do also have an s orbital that relates to helium on the right-hand side of the periodic table. This is the second s orbital in our first row. We have 6 p electrons that we can put into our p orbitals. This is 3 p orbitals, each with 2 electrons, 1 spin up and 1 spin down. The d orbitals are for our transition metals, and we can put 10 electrons into these d orbitals, and the f orbitals are located on the very bottom of the periodic table, 2 rows that sit below the periodic table. So let's look at the electron configuration from the periodic table. If we want to write the electron configuration for phosphorus, there are 2 ways that we can do it. One is a longhand version, or the full electron configuration, and one is shorthand. We're going to start with the full electron configuration. So for phosphorus, we start by reading at the upper left-hand side of the periodic table, and we go through the 1s orbital with 2 electrons in it. So we write the 1s orbital and a superscript of 2 showing us that that s orbital is completely filled. Now we start again at the left-hand side, and we go through the 2s orbital, and that is going to be completely filled because we haven't reached phosphorus yet. We continue reading across the periodic table, and this would bring us to the 2p orbital, which is going to have 6 electrons in it because it's 6 blocks long, and we have not gotten to phosphorus yet. Go back to the left-hand side. We are in the 3rd energy level. We're traveling through our s orbital. So 3s. We haven't got to phosphorus, so that is filled with 2 electrons. S orbitals always hold a maximum of 2 electrons. P p orbitals always hold a maximum of 6 electrons. The orbitals can hold a maximum of 10, and f a maximum of 14. Now we're going to enter into the 3p orbital, but we're not going all the way through it. So if we count the boxes, we go 1, 2, 3 boxes to get to the phosphorus. So it would be 3p3. Alternatively, so this would be the longhand version. Alternatively, we can write a shorthand version starting with the noble gas in the row above it. So the noble gas in the row above it is neon. And neon is going to represent all of our core electrons. So everything up to the 2p. We write it in brackets. Now we're going to read left to right. We're going through the 3s orbital with 2 electrons in it. And then we travel into the 3p orbital. Again, we're still traveling 3 boxes. So our shorthand notation is going to be 3s2, 3p3. Now, if we want to determine the number of valence electrons, we are looking at our highest energy level, which is the 3rd energy level, and adding up all the electrons in the 3rd energy level. So we would have a total of 5 valence electrons. To draw our orbital diagram, s orbitals always have one line. And if we're writing the short orbital diagram, again, just starting at the noble gas, our 3s orbital is completely filled, so we would have 2 electrons in it. The p orbital has 3 different orientations that it can be. We have 3 electrons that we're putting in, and Hund's rule tells us that we can only put 1 electron, or we have to put 1 electron into each orbital before we start pairing them. So we would have 3 unpaired electrons in that 3p orbital. Transition metals are determined the same way, with one little thing that we need to remember. That is that whenever we go into the D block, it is actually 1 less than the row it sits in. So the energy level that it belongs to is 1 less than the row it sits in. So if we're looking at row 4, it is actually the 3d orbital. So if you look at zinc, zinc is number 30. We would start at argon, it is 4s2, but then because we're entering the d orbital, it is 1 less for the energy level, and so it would be a 3d10. If we go into the F block, the F block is 2 less than the row it sits in, and they actually belong in row 6 and 7. And so when we're writing it for anything with 4F, it would be, our example is europium, would start at xenon, it would be 6s2, 4f7. And again, when we're writing our orbital diagrams, our d orbital has 5 orbitals that we're putting electrons into. The f orbital has 7 that we're putting electrons into. So the d orbital is 1 less, f orbital is 2 less than the row it sits in. So let's try an example. So now we have arsenic. We're going to write shorthand electron configuration. We're going to start at argon. We travel through the 4s orbital, and it is completely filled, so it's 4s2. We now travel through the D, which is 3d10, and then 3 blocks, and we do return to the 4th energy level once we pass through to the other side, and it becomes 4p3. Now, arsenic also has 5 valence electrons, and these come from the 2 in the 4s, and the 3 in the 4p. Because the 3d10 is a lower energy level, they do not count as valence electrons, just the highest value, the highest energy level. Here's a practice for you to try. Use your periodic table to write the shorthand electron configuration and the short orbital diagram for the following elements. Pause the video to determine your orbital diagram and electron configuration. Sodium is number 11. So for our electron configuration, we would start at neon, and it would be 3s1. Our orbital diagram would be the 3s orbital with a single electron pointing up. If we look at tellurium, tellurium is number 52. So tellurium, we're going to start at krypton. We go through the fifth energy, 5s2. We go into now one less than the energy level we sit in. So it would be 4d10. We come out the other side and we're back to the fifth. So 5p4. If we draw our orbital diagram, the s orbital gets one line. Make that a little neater. 5s. Our 4d is going to be 5 lines long because d orbitals there's always 5. And p orbitals there's always 3. So our s orbital would be completely filled. Our d orbital would be completely filled with 10 electrons. And our p orbital, we would put one in each of the p orbitals before we start pairing them. So we would have one set of paired electrons and 2 unpaired. Now if we look at technetium, technetium is number 43. We would start at krypton again. We would travel through 5s. We would go into the 4d, but now we did not completely fill the 4d. We count the blocks over till we reach technetium, and we end up with 4d5. If we draw our orbital diagram, we'd have one line for the 5s, 5 lines for the 4d. Our s would be completely filled, and the 4d would have 1 electron in each of the orbitals. There are some irregular electron configurations. These are what we would expect looking at the periodic table. What we actually see, found experimentally, is that we can actually, for chromium, we promote one of the s electrons into the d. The reason this happens is now we have a half-filled orbital for both the s and the d orbital, and there's extra stability from it being half-filled. We also see this with copper, but now we promote one out of the s orbital. We have a half-filled and a completely filled orbital, which adds to the stability. See this for molybdenum as well. Now, if we look at anions in their ground state just means all the electrons are in the lowest energy level possible. We want to form an anion. We're adding electrons into the anions that are formed from the nonmetals so that there are enough electrons to have 8 valence electrons. So we fill the s and the p sublevels of our valence shell. So if we start with sulfur, which has 6 valence electrons, in order to have 8, it's going to gain 2 electrons to become S2 minus. So now we have 3s2, 3p6 for a total of 8 valence electrons. This is why knowing the position on the periodic table helps us to determine the charge. If we look at cations in their ground state, we're going to go the other way. So we're losing electrons. We're going to lose them out of the highest energy level, and we're going to remove them to become like the noble gas that is in the row above. We have a new lower energy level valence shell, but it does take a little bit of energy, so it is an endothermic process in order to remove the electrons. So if we look at magnesium, 1s2, 2s2, 2p6, 3s2, we are going to lose the 2 electrons from the 3s orbital. So now when we look at its electron configuration, it has the electron configuration of neon.